Hi, let's discuss single source shortest path. One source is given, multiple destination is given. We want to find shortest path from single source to multiple destination. Let this is the source. We want to find shortest path from single source to multiple destination. So that is called as single source shortest path. Take a real life example. Recently Halloween finished. Suppose I want to see Halloween lights, I will search Halloween lights near me and it will show multiple option, multiple location. Then I will see the distance from my home to that location and whichever the shortest I will go. It will show multiple places and according to time and according to the distance then I will choose and I will visit. So in a shortest path problem, we are given a weighted directed graph g equals to VE. Weight are given and direction are given. With a weight function W, E implies R mapping S to real valued weight. So the weight of the path WP equals to V0, V1 up to Vk is the sum of the weight of its constraint edges. Or you can say WP equals to sum of I equals to 1 to K W Vi minus 1 up to Vi. Suppose we want to find path cost from V1 to V3. There is another vertex V2 in between it. Suppose V1 to V2 cost is 2, V2 to V3 cost is 3. Then V1 to V3 path cost will be 2 plus 3, it will be 5. We can define shortest path by del UV. So del UV equals to minimum path cost from U to V if some path is present. If no path, then it is infinitive. A shortest path from vertex U to vertex V in any path with weight we can write as WP. WP equals to del UV. Del UV is the distance, WP is the weight of that path. So weight of that path equals to distance from U to V. I already discussed breadth first tree. By breadth first tree, you can find shortest path from root to every vertex, but that was for unweighted graph. Or you can say every weight are same. But here for weighted graph, how you can find the shortest path? There are some variants. First, single source shortest path problem. Given a graph g equals to VE, we want to find shortest path from single source S belongs to V to each vertex V belongs to V. So the uppercase V is for set of vertices or all vertices of the graph. The small v is for single vertices. Next, single destination shortest path problem. Single destination shortest path problem means one destination is given, we want to find shortest path from different source to that destination. Suppose this is a destination T, we want to find shortest path from different source to that destination. So we can reverse the single source shortest path, means we can make this destination as source and we can find the shortest path. So by reversing the direction of each edge in the graph, we can reduce this problem to single source problem. So single source shortest path. Next, single pair shortest path. Find a shortest path from U to V for a given vertices U and V. So that is single pair shortest path. If you want to find shortest path between a pair. Next is all pair shortest path. Find a shortest path from U to V for each pair of vertices U and V. If we are finding shortest path between every pair of vertices, that is all pair shortest path problem. Floyd-Warshall algorithm is for all pair shortest path, while Dijkstra algorithm is for single source shortest path. Dijkstra algorithm is a greedy technique and the Floyd-Warshall algorithm that finds shortest path between all pair of vertices is a dynamic programming algorithm. After this chapter, I will discuss dynamic programming. There I will discuss all pair shortest path. Next is negative weight edges. Dijkstra algorithm don't allow negative weight edges. It consider all edges are positive, while Belaman-4 algorithm allow negative weight edges in the input graph. So Belaman-4 algorithm allowed negative weight edges, and if there is a negative weight cycle on some path S to V, we define del of sv equals to minus infinitive. As every time it will be reduced, so we can define it as minus infinitive. So if negative word cycle present, Velaman for algorithm will detect and report that negative word cycle present. If no negative word cycle present, it can find the shortest path from source to every other vertices like Dijkstra. Next, representation of shortest path. We not only compute the shortest path weight, we also compute the path, means through which vertex it is reaching to destination. So we keep a track of all the vertices. We maintain a pi attribute. That pi attribute keep track from which vertex we reach to that vertex. Or we call it as a predecessor. V dot pi is either another vertex or nil. Suppose from U you are reaching to V, then V dot pi equals to U. From which vertex you are reaching to vertex B. Let's see an example. This is a graph. Now we'll see shortest path from S to every other vertex. So this is one shortest path. From S to T, shortest path is 3. From S to X, shortest path is 9. So here cost is 9 and this is the path 3 plus 6 equals to 9. From S to Z, cost is 11. 5 plus 6 equals to 11. There is also another shortest path possible. Here you can see from S to Y, cost is 5. From S we are going to T, from T we are reaching to Y. Here S to Y direct path, here via T. Then S to X, here we reach S to T, then T to X. While in the second graph from S to T 3, then T to Y 5, then Y to X. So 3 plus 2 plus 4 is 9. You can mark in both shortest path graph, cost are same. Here y cost is 5, here also y cost is 5. But in first graph S to y directly we are going, while in second graph S to t, then t to y. So there can be multiple paths possible. Next I will discuss relaxation. Relaxation is important for understanding both Dijkstra and Velaman for algorithm. So for each vertex V belongs to V, we maintain an attribute V dot D. D means distance, or we can say sorted path estimate. Means till that vertex B, what is the cost? We initialize the shortest path estimate and predecessor by following order of V time procedure. So initialize single source G S. G is the graph, S is the source. For each vertex V belongs to GV. For each vertex, this small v per vertex, GB means graph all vertex. BD will be infinitive. Then B dot pi equals to nil. B dot D means cost of that vertex equals to infinitive. B dot pi means predecessor of vertex B equals to nil. S dot D equals to 0. So distance for source will be 0, rest all other vertex distance will be infinitive and its predecessor will be nil. So the process of relaxing an edge UV consists of testing whether we can improve the shortest path to V found so far by going through U. If so, then we'll update distance and predecessor. So the following code perform relaxation step in order of one time. Relaxation U V W. If V dot D greater than U dot D plus W U V, then V dot D equals to U dot D plus W U V and V pi equals to U. Just take an example. This is U V. U cost is 5, V cost is 9. So V dot D means 9 greater than 5 plus what is the weight of this path, that is 2. Is 9 greater than 5 plus 2? Yes, 9 is greater than 7. Then we'll update means B dot D equals to 7. So this cost will be updated. Previously it was 9, now it is 7. Suppose it is not greater than, like this here, V cost is 6. 6 is not greater than 5 plus 2. So will not update, it will be as it is. If vertex B distance is greater than vertex U distance plus path cost of UV, then only we are updating. If it is not greater than, there will be no change. In today's lecture, I discuss what is shortest path, what is relaxation. In next lecture, I will discuss Bellman for algorithm. If this lecture is helpful for you, please like, share and subscribe. Thank you.